In this video, I'd like to show an example of integration by parts. Before looking at the example, you need to know the formula of integration by parts as shown. Make sure that integrand must have the product to use this formula. However, the product form doesn't mean to use this formula all the time. Let's take a look at the example. In this example, there is a product of x squared and cosine x dx in the integrand. Does simple u-substitution method work for this example? In order to use the simple u-substitution method, the relationship between two functions must be the original and its derivative each other except for constant. Unfortunately, x squared cannot be the derivative of cosine x, or cosine x cannot be the derivative of x squared either. Therefore, we cannot use the u-substitution method here. Then let's try to use integration by parts method. Let's match up the left side of the formula with the integrand of the question. In this method, we need to separate the product into u part and dv part. According to the formula, we need to decide which function should be u part or dv part. Which function becomes simpler if you take the derivative? If we differentiate x squared, then the derivative is 2x. And if we differentiate cosine x, then it becomes negative sine x. Since 2x is lower degree than the original x squared, we can say that the derivative becomes simpler. On the other hand, the derivative minus sine x is the same level as cosine x function. Therefore, u part should be x squared and cosine dx part should be dv part. Make sure we need to include dx for dv part. Let's fill in the table. Since we decided x squared as u part and cosine x dx as dv part, I placed u equal x squared, which is the original function, on top, and the differential dv part at the bottom of the table to be organized. Now, differentiating u equal x squared to get 2x dx as du. One more box, we need to find one more function v. Since v is the original function of dv, integrating dv part to get sine x plus c. However, we do not have to include the arbitrary constant c at this moment. So v equals sine x. Now we have all four functions ready. Let's apply the right side of the formula. First, for the product of u and v, multiplying x squared and sine x to get just x squared sine x. Next, be sure that there is a minus symbol. For the last part, there is an integral symbol in the formula. So the integral of v du becomes 2x sine x dx. If we take a closer look for the integrand, we can see the product of two functions again. Since we cannot use the u-substitution method, apply the integration by parts formula again. Using the same argument before, as u part becomes simpler when taking the derivative, u part should be 2x and dB part should be the sine x dx this time. Let's fill in the table. Since we decided 2x as u part and sine x dx as dB part, I placed u equal to 2x, which is the original function, on top, and differential dB part at the bottom of the table. Now, differentiating u equal to 2x to get 2 dx as du. As for v, integrating dB to get minus cosine x plus c. As same as before, we just use the function part v equal minus cosine x here. Now we have all 4 functions ready for the second application of the formula. Let's apply the right side of the formula. Copy the original uv part as x squared sine x, and let's enclose the work for the second time application of the formula. For the new product of u and v, multiplying 2x and minus cosine x to get just minus 2x cosine x. Next, make sure that there is a minus symbol. For the last part, there is an integral symbol in the formula. So the integral of v du becomes minus 2 cos x dx. Let's remove the bracket and simplify the equation. Removing the bracket to get x squared sine x plus 2x cosine x minus 2 integral of cosine x dx. Make sure that we still have the integral symbol, which means we have not finished this question yet. We still need to integrate the last part of the equation. Using the integral of cosine u du formula, we get minus 2 sine x plus c for the last part of the equation. So finally, we get the solution as x squared sine x plus 2x cos x minus 2 sine x plus c. If you want to make sure if this is a correct solution, then try to find the derivative of the solution. You should get the derivative as x squared cosine x, which is in the integrand. Thank you for watching. See you next time.